We all enjoy a nice cup of coffee, and even more so due to the beautiful pattern of milk and coffee on top of it. The alternate bands are formed of coffee and milk and appear to be a kind of folding and stretching pattern.
Hello, my name is Aditya, and today we are going to find out what the link is between the folds of metamorphic rocks and a cup of cafe latte. But before that, let us see what fluid mechanics is. It is the study of fluid statics, that is, fluids at rest, and fluids in motion, that is, fluid dynamics. Fluid mechanics has a large bearing on day to day life. For example, the water stored in a dam can be used for irrigation, for hydroelectric power generation, and fisheries. Fluid mechanics helps us to design ships and other floating objects such as oil rigs. We practically live in a fluid, that is atmosphere. The dynamics of the climate has a huge bearing on life as we know it. The majority of the planet is covered by oceans, which is nothing but a mixture of salt and water and other chemicals, of course, and it bears tremendous life forms, most of which we still haven't uncovered. Fluid mechanics gives us pointers to help us understand the transmission of diseases during events like sneezing or coughing. Biologists are also interested in understanding how fishes swim, survive, how birds fly, how insects travel along water, along air. In fact, fluid mechanics is quite important for us in a very strong engineering sense because most of the things that we make use of have some kind of basis in fluid mechanics. For example, the operation of a car or the flight of an aeroplane, not just how aeroplanes fly, but the way they generate the thrust through turbines. Everything depends on a solid understanding of fluid mechanics. Understanding the melange of fluid mechanics, heat transfer, and thermodynamics is at the core of any power plant and essentially is driving industrial revolutions in many countries. But going beyond these kind of applications and studies, fluid mechanics also finds its way in certain arts. Two examples are shown over here. The first one is Starry Night by Vincent van Gogh, which depicts the vertical structures of the atmosphere. The second photograph is by Leonardo da Vinci, in which he shows how a jet falling into a pool shows decay through means of dissipation through eddies. It is very important to understand that these kinds of initial works laid the foundations which were purely observational for other mathematicians to follow. Very famous mathematicians and physicists have tackled various problems in fluid mechanics. The list shown here is by no means exhaustive, but it is just a collection of names which are quite famous, and I have no intention of leaving out anyone who was important. It's just what I could think of at the spur of the moment. So, developments in fluid mechanics were laid by Euler, Lagrange, Cauchy. Various foundations of inviscid flows were laid down by Bernoulli. In modern times, Kolmogorov laid down various elements of turbulence. Sir James Lighthill gave insight into dynamics of flying, swimming, and so on. Various physicists have also contributed tremendously towards understanding of fluid mechanics, starting from the works of Navier and Stokes. Einstein undertook a lot of work in understanding suspension dynamics. Heisenberg's earlier works were on turbulence and instability. Sir G.I. Taylor and Batchelor worked extensively on various aspects of mixing, turbulence, low Reynolds number flows, and so on. Dijon was awarded the Nobel Prize in 1991 for his pioneering work on polymeric fluids. The famous Indian physicist Subramaniam Chandrasekhar also did a lot of work on instabilities pertaining to magnetohydrodynamic flows. Matter can be classified as solid, liquid, or gas. Liquid and gas can be cumulatively labeled as fluids. Fluids can deform continuously under the action of a shear, which means that when you have a fluid element as shown and you continuously subject it to shear, it deforms and keeps on deforming. Even if you remove the shear applied, it will retain the final shape. Solids can resist such kinds of shear forces in the sense that once you remove the shear force, it gets back to its initial condition, provided that the solid is completely elastic. Liquids hold no preferred shape, in which means that if you pour a liquid into a glass or a container, it will take the shape of the glass or container. A corollary of the first statement is that a liquid at rest will have no shear forces acting on it. It means that if liquid at rest were to have some kind of shear force, it would deform and therefore it will no longer be a fluid at rest. Let us move to another concept, which is the concept of a continuum. Let us recall that in Newtonian mechanics, we have the governing equation which says that the velocity is the rate of change of position. So dx dt is v x, dy dt is vy, and dz dt is vz. And the next statement is that the net force is equal to the mass times acceleration, and therefore we can write that fx will be equal to m times dvx dt, fy will be m times dvy dt, and fz will be m times dvz dt. If we combine the first two statements, we obtain a second order differential equation which relates the position and the force, and obviously these must have some kinds of initial conditions. Now, depending on the initial condition, if we track a particle, we will have the evolution of particle and the trajectory. So we will have how the velocity will evolve, and we will also have how the position will evolve. Now consider four different particles. We must first determine the forces acting on particle 1 due to 2, 3 and 4, on 2 due to 1, 3 and 4, on 3 due to 1, 2 and 4, and on 4 due to 1, 2 and 3. We must then solve, in fact, the equation that we have shown earlier to find out the trajectories for each of the particle. Now, as the particle distances will change because they are changing their positions, we must then recalculate the forces. This entire procedure will continue. But how are the forces calculated? So if we consider planetary systems, the forces are obtained as g m1 m2 by r square, where r is the distance between two particles. For electrostatic systems, we can find out the force as q1 q2 by r square. It's proportional to q1 q2 by r square. But what about for molecules? Well, in the case of molecules, we have something called as a Lennard-Jones potential, the gradient of which gives us the force. So for now, it is important to just know that the Lennard-Jones potential has a form which is 1 by r to the power 12 minus 1 by r to the power 6. So given an initial configuration of molecules, we then can use the Lennard-Jones potential to find out the forces acting between each particles. Once we have that, we can evolve the molecule velocity and position. But let us consider 1 mole of an entity that will contain 10 to the power 23 entities of that matter. So for example, if we have 1 mole of oxygen, it will contain 10 to the power 23 molecules of oxygen. Now if we consider a computer which has a ability of 1 gigaflop, that is 10 to the power 6 floating point operations per second. So it means it will require something of the order of 10 to the power 17 seconds, even if I can have one sort of calculation per molecule going on. And that really shows that This entire process is really impossible to calculate within a given reasonable time. Of course, it is possible for small systems where there are 1000 molecules or 10,000 molecules, where you can have GPU accelerations and so on. So, what do? We consider an observation window with a sufficiently large number of molecules. We say that there is a statistically large number of molecules in the observation window. Then we can average out various quantities. So, the average number of molecules in that observation box will give us the density of that particular observation box. The average kinetic energy of all the molecules in that box is the measure of temperature of that box. Of course, molecules are free to come in and go out, but we are worried about the average taken at a given instant of time. And the average number of collisions on a surface of the box is a measure of the pressure. We know this from elementary statistical and ideal gas mechanics. So once we do such kinds of averaging, we can sort of forget about what the box comprises of and represent the box as such kinds of field operators. So instead of defining each molecule separately, we will say that look, this small box is my lowest unit of measurement, and this box has a density, has a temperature, and has a pressure. I need not again describe the entire motion of molecules inside the box. Let us consider a box in which there are only two molecules. So initially the density is 2. If one molecule leaves, the density will become 1, and if two molecules come in, the density will become 3. So you see that the density that we calculate using this particular small box will fluctuate very wildly over time and will not give us a reliable estimate of what the density is. Let us consider the other case where the observation box is of the size of, say, a room. Let us consider that the room has a candle lit on one of its end. Because of the candle, the hot air, there is some hot air near the candle and there is some cold air near the ceiling. So we know that because of this kind of a temperature distribution, there will be a hotter air near the bottom and colder air near the top. So the density at the lower part of the room will be lower, and the density at the upper part of the room will be higher. So if we choose the observation box to be so large, we will sort of smother out any variation in density that we were interested to measure. Essentially, the box is so large that whatever variation there were are being smoothened out. So even having a large box is not beneficial. If we plot the density as a function of the observation volume, we will see that when the observation volumes are small, the density will fluctuate wildly. Whereas there will be a point after which the density will have a fixed value. That is the region in which we have an appropriate measuring volume which gives us consistent results. Beyond a certain volume, again, we will have macroscopic variations in the observed density, which really are not the kinds of observations we are interested in. So, if we consider typical systems, the length of a observation box, should be 50 nanometers. So, in that case, if we have a room which is 1 meter wide, we will have 8 orders of magnitude between the smallest size of the box that we can have and the size of the rooms. So if there is a candle, if we consider the room being split into 50 nanometer boxes, we will see that for an observer who cannot resolve 50 nanometers, the room will seem like a continuum, and we can define a continuous field of temperature or density or whatever quantity you want to measure. Essentially, we have removed the description of discrete particles and replaced them as continuous variables. This is called as the continuum. It is like watching a television from a very large distance. You see every image to be a very smooth image, but the moment you go near a television and see what really going on, we can see those small pixels, and those pixels are sort of the volumes that we are concerned about. And when we look at small pixels on a large screen, is exactly what we have. We have an abstraction of discrete entities in the form of a continuum. But is the size of the box the only parameter that is important? The answer is no. Consider the system in which the box, the physical box, not the box of measurement, physical box has this particular size L, and the molecules have a mean free path lambda. So mean free path means that that is the distance that a molecule will travel before encountering a collision with another molecule. So if the mean free path is much smaller than the length of the room, that is, the room is much larger than the mean free path, then you have a situation in which molecules are colliding more frequently than it will encounter the wall, and therefore we can assume that the description of such a system will not be on a molecular scale. On the contrary, if the mean free path is larger than the length of the room, before a molecule will collide with another molecule, the molecule will collide with the wall of the container. This means that the flow inside is not a continuum flow, but it is more like a free molecular flow, where you, instead of having continuous variables, you still have discrete entities bouncing around, because rather than having collisions with themselves, they are having collisions with the wall. As a matter of fact, these analysis and these abstractions of continuum are not just restricted to gases and liquids. They are also valid for analyzing crowds of people. If you look at what a Mexican wave is, it is a huge crowd of people which actually resemble a traveling wave. And because there is a large amount of people in a very small area, each person is sort of encountering another person rather than having a large distance between themselves. Therefore, the motion when seen from a far distance will appear to be continuous, and therefore one can actually apply certain kinds of continuum mechanics aspects to analyze such kinds of Mexican waves. Interesting. So let us get back to the question. Does a solid really flow? What is the relationship between a metamorphic rock and the coffee art that you see on the cafe latte? We know that solids begin to flow when the amount of stress that it is subject to crosses what is called as the plastic deformation zone. It is beyond the linear elastic zone. And in fact, various kinds of fluids, which are mixtures of certain kinds of colloids or polymers, they have a tendency to behave both like a solid and a liquid. And we know this from common experience that things like ketchup, cornstarch, blood, drilling fluids, these kinds of fluids behave very weirdly. They don't exactly behave like fluids, and they don't exactly behave like solids as well. And the area of study which pertains to such kinds of matter is called as rheology. The origin of the word rheology can be traced back to the phrase manta rei by Heraclitus, which means everything flows. So while the original phrase was purely philosophical, the subtext can be applied to anything, in the sense that various matter which may seem solid, which may ordinarily seem solid, but are actually liquids. What differs are the time scales. We have gone past the length scale and now we are entering the discussion of a time scale. We consider the very famous experiment at the University of Queensland, in which Pitch is dropping from a top container into a petri dish. So pitch or bitumen has a viscosity which is 11 orders of magnitude larger than the viscosity of water, which means that ever since the experiment first started, there have been only 8 drops of pitch, and the 8th drop was in the year 2000. And it takes a huge amount of time for pitch or bitumen to form a drop and fall into the container. If you look at it for even a month, you will almost see no movement, nothing going on. So you may conclude that it is a solid. But if you take a time lapse photograph over say 20 years or 30 years, and if you compress the time lapse photograph into a very small time, say 10 seconds, you will actually see that yes, it is trying to drip like a fluid. So time scales also matter. Let us consider what happens to metamorphic rocks. So there is some kind of an original base rock, so it can be a sedimentary formation, okay, and usually in order for rocks to flow, we need to overcome the very strong attraction force in which resembles Arrhenius equation, which you might have studied in chemistry. So e to the power minus activation energy upon kT. So if activation energy is very large compared to kT, it means that you need to wait for a huge amount of time, and that the reaction, I mean in the case of Arrhenius it is the reaction, while in this particular case it is the bond breakage. It will be extremely slow, but it will still be finite. Despite it being extremely slow, it will still be finite. Increasing the temperature and pressure leads to a reduction in the activation energy, allowing for the bonds to be broken and the flow to occur. So if we have sediments like this and there is some kind of high pressure and temperature, it leads to a deformation over several years, over hundreds of years in fact. And that kind of deformation is what is done in order to form the art on a latte, and that takes around 10 seconds. So in conclusion, both metamorphic rocks and the cafe latte are formed out of folding and stretching patterns, but the only difference is the solid flows over a time scale of 100 years, whereas the liquid flows over a time scale of 10 years. And yes, solids under various conditions can be considered as liquids. With this, we conclude this particular session, and I will see you next time with a new topic. Bye.